In this video, we're going to look at specific Pythagorean theorem problems which involve circles. So, before we try problems that involve circles and right triangles, we need to recall some circle and tangent and chord conjectures from the previous unit. So, first, a tangent to a circle is blank to the radius drawn at the point of tangency. So the question is asking, what's the relationship between this tangent line and the radius that intersects the point where the tangent line is tangent to the circle? And hopefully you recall, or you see, that the blank would be perpendicular. So, let me write that down real quick. If you ever have a tangent drawn to a circle and there's a radius intersecting that point of tangency, those two segments will be perpendicular. Alright? And the reason why it's important is because that's a right angle. If I just drew a line like that, I have a right triangle now. So now it becomes a right triangle circle problem. Let's look at a second conjecture, and this is the angles inscribed in the semicircle conjecture. Angles inscribed in a semicircle are blank. So here is a circle. Here's the center. So this diameter will cut the circle in half. If I inscribe an angle in the circle, and this arc is 180 degrees from here to here, then what do I know about this angle in red? Well, hopefully you see that it is a 90-degree angle, because inscribed angles are always half the measure of the arcs they intercept. So if there's an angle inscribed in a semicircle, which is also a better name for a 180-degree arc, then that angle is going to be 90 degrees. So angles inscribed in a semicircle are 90 degrees. One last conjecture that we need to review is the chord conjecture. The perpendicular radius of a circle to a chord is the blank of a chord. So what this is saying is, let's say you have a circle and the center and a chord. If I draw a radius from that center so that it's perpendicular to the chord, what else is special about that chord? So if I went straight up so that this radius intersected the chord at 90 degrees, then it's also going to cut the chord in half. Alright, and just to show you why that works, let's look at a counterexample. Let's say that I drew a radius that wasn't perpendicular to that chord. Alright, so we have an acute angle right here. Well, it's also not going to be the midpoint of that chord. So the perpendicular radius of a circle to the chord is the bisector of the chord as well. Alright, so let's try some problems using these conjectures. So the first one is right here. So we have a circle with radius OC, and the first thing that we're given is that OC and AB are perpendicular. So it says it right there. I'm going to change up the color real quick, and I'm going to draw that on my picture. It also says AB is 24 in the next step. So since that whole chord is 24 and OC is perpendicular to AB, then OC is going to cut that chord in half. So AM is going to be 12, and so is MB. It also says MC is 8. So from here to here is 8. Find the diameter of circle O. So what can we do here? Well, if we draw this OB right here, that would be a radius. And it would also form a right triangle, OMB. And we know one of the sides is 12. We don't know OM, so let's call it X. And the reason why I did that is because now I can express the radius as X plus 8. Because from here to here is X plus 8. And so is from here to here, because they are both radiuses, from O to B and from O to C. So since the radius is X plus 8, now I have enough information to set up the Pythagorean theorem. So if I said a squared plus b squared equals c squared, then I would have x squared plus 12 squared equals x plus 8 in parentheses squared. So now this is going to turn into a quadratic. So if I expand, well, first x squared is x squared. 12 squared is 144. And if I expand out the right side, I have x times x is x squared, and then x times 8 is 8x, and then x times 8 is 8x again, so that gives me 16x, and then 8 times 8 is 64. If you don't understand how I got this, I suggest you go back to the previous step, pause the video, and write out x plus 8 times x plus 8 and FOIL that. And you'll hopefully get x squared plus 16x plus 64. So make sure you know how to do that. Alright, now we want to try to solve this, so let's get x alone. So if I subtract x squared on both sides, that's going to cancel out my x squareds. And then if I subtract 64 on both sides, then on the left side I have 144 minus 64, which would just be 80. And then on the right side, the only thing left is 16x. If I divide both sides by 16, then I get x is 5. And if we look back at our diagram, that answer makes a lot of sense, because then I have this leg right here, which is 12, this leg right here, which we know is now 5, and the hypotenuse, which is x plus 8, 5 plus 8 is 13. So I have a right triangle with side lengths 5, 12, and 13, which is a Pythagorean triple. So if you knew that, you don't even need to plug that back in to see if it was the right answer, because you know it is. So let's try another one. Alright, this one says, find the distance from R to H. So notice how that is not drawn yet. So let's draw that line RH that we're looking for the distance of. And it also says that HA is 6. And we also know that this is a radius, and so is that. So AR and RT are radii. And since H is a point outside a circle where two tangent segments are drawn to the same circle, HA and HT, we know that both of these segments are equal. So AH equals HT, AR equals RT, and we know AH is 6, not 60. Little typo there. Let's erase that. So HT is going to be 6 as well. So we didn't really learn a lot about kites. Actually, we didn't learn at all about kites. But this is a kite because it has consecutive sides that are congruent. And what's special about kites is that the diagonals will bisect each other. So RH is going to divide angle ART, which is 120 degrees, into two congruent angles. So that's going to be 60, and that's going to be 60 as well. So we also have a radius intersecting a tangent segment. So both of these angles will be 90 degrees, angles A and T, because again, whenever a radius intersects a tangent, it'll be 90 degrees. So if you subtract those two angles from 180, you get that the remaining angles are 30. So this is a 30, 60, 90 triangle where we know the long leg, right? If you look at just this 30, 60, 90 triangle, which I'm going to highlight in yellow, the side opposite the 60 degree angle is 6. And it's asking from the distance from R to H, which is the hypotenuse. So all I have to do is first divide 6 by root 3 to get my short leg, so then I could double it and find the hypotenuse. So my short leg is going to be 6 over root 3, which if I simplify by multiplying the top and bottom by root 3, I get 6 root 3 over 3, which just becomes 2 root 3. So this side right here is 2 root 3. If I want to know the hypotenuse, I'm now going to double it to find double 2 root 3 to find the hypotenuse. So I get 4 root 3. And that is my final answer. Alright, let's try one more. If you're starting to feel good about this stuff, I suggest you pause it and try to do these 3, or maybe watch the first one and pause it for the other 2, and then hit play when you want to see an answer. So, it says that JT is tangent to circle O at T. Complete the following. So if OT is 6, so let's label our picture, and JO is 10, so let's draw that out, then find JT. Well, since we know this is a radius and since we know it's a radius and a tangent, that angle is going to be 90 degrees. So you can do the Pythagorean theorem and solve for JT by doing 6 squared plus x squared equals 10 squared. Now, if you know that 3, 4, 5 is a Pythagorean triple, then 6, 8, 10 is also a Pythagorean triple. So if you knew that, you don't even need to finish solving this. You would know that JT is 8. But if you don't, then I would just pause the video real quick and finish solving it. Alright, let's do the next one. I'm just going to clear everything off so it's a little less confusing. So now we're here. So it says OT is 6 and JT is 10. And we remember that this angle is 90 degrees because it's a radius and a tangent. So it's saying find JL. So let's draw it. Well, now we need to use the Pythagorean theorem because 6, 10 blank isn't a Pythagorean triple. So we have 6 squared plus 10 squared equals x squared. And then 6 squared is 36. 10 squared is 100. Aw, man. I accidentally exited this slide. We can fix that. I apologize. Technical difficulties. Alright, well anyway, back to where we were in this problem. You get it down to x squared, and we're on this second problem right here. You get it down to x squared equals 136. So x is going to equal the square root of 136, and then try to simplify that. And after trying to do some factoring, you'll see that 4 goes into 136, and it goes into it 34 times. So you can rewrite the square root of 136 as just 2 root 34. So that's going to be the answer to the second question. And then the last question, it says if you know TOJ, so this angle right here, this angle right here is 60 degrees, and OT is 6, find JO. Well, OT is 6, and it's also the short leg in a 30, 60, 90 triangle. Alright, that angle is supposed to be 30, not 36. Because we know this angle is 90, the given angle was 60, so the remaining angle has to be 30 in order for those three angles to add up to 180. So, if you know OT is 6, JO is just the hypotenuse, so you're just going to double it, and you get that the hypotenuse JO is 12. Alright, one last problem, and that is to determine whether MN is tangent to circle L. So, good question. So first let's start off by adding stuff to the diagram that we can assume. Well, we can't really assume that this angle is 90 degrees because it doesn't say if MN is tangent. It's asking us to find out if it's tangent. So we don't want to use that in our reasoning. So one thing that we know is that all radii in circles are equal. So if LM is 3, then LO is going to be 3 as well. Well, if this angle is 90 degrees, then MN is tangent. So we can use that to our advantage, but we can't assume that it's 90 degrees. We have to prove that it's 90 degrees. And the way we're going to do that, so let's erase this 90 degrees thing. The way we're going to prove that that angle is 90 degrees, or prove that it isn't, is to use the converse of the Pythagorean theorem. If you notice, the two radii and the two additional segments form this right triangle right here. So we can use the converse of the Pythagorean theorem to test those side lengths and see if a squared, so this could be a, plus b squared, that could be b, equals c squared, which is 5. So if you know that's a Pythagorean triple, then you're done, and you know it's going to form a right triangle and make MN tangent to circle L. But if you didn't see that, let's show why. So if you take a squared plus b squared, you get 3 squared plus 4 squared, which is 9 plus 16, which is 9 plus 16, which comes out to 25. Alright, if you take c squared, that's 5 squared, that also comes out to 25. So since a squared plus b squared equals c squared, then you can assume angle M is 90 degrees, which says that yes, circle L is tangent. Okay, so since that line is tangent to the radius, that means that it is perpendicular to the radius, and we proved it using the converse of the Pythagorean theorem, then that means that that line is tangent to the circle. Alright, hope that video was helpful. Sorry for it being a little long. Please email me if you have questions, and have a good one.